Yes. In the previous lecture, we were discussing about the system of first order differential equations. We discussed what is a system of first order differential equation, how to represent that system in a matrix form. What was the matrix form of any linear system of first order differential equation? It was a kind of dx by dt is equal to a times x, where x is some vector which contains all the unknown variables of that differential equation, which is x1, x2, so on, xn. And it is, remember that it is n cross 1 vector. And this matrix A was the coefficient matrix, and its order was, it has entries aij, and its order is n cross n. So this was a system of first order differential equation. It is homogeneous system, and its coefficients are constants. Means the matrix A is a constant matrix. We discussed that we are going to solve this kind of systems. This was the matrix form of that system, and we also discussed superposition principle for finding the general solution of the system of differential equation, and in order to check whether the solutions are linearly independent or they form a fundamental set of solutions, we also discussed the Wronskian. Wronskian was what it was: x11, x12, so on, x1n, x21, x22, so on, x2n, so on, xn1, so on, xn2, so on, xnn. So this was the Wronskian, and we discussed that the Wronskian should not be zero for all values of p belongs to some interval I. Okay, this was the definition of Wronskian in order to check whether the given set of n solutions are linearly independent or not. If the solutions are linearly independent, then we say that those solutions form a fundamental set. Fundamental set was basically fundamental set of solutions. It was kind of x1, x2, so on, xn, where x1 was what? X1 was some k vector times e raised power lambda 1 t. X2 was what? X2 vector, k2 vector lambda 2 t, and so on, xn is equal to kn e raised power lambda n t, where what was these vectors k1, k2, so on, kn, and what was these constants lambda 1, lambda 2, lambda n. These lambdas are eigenvalues, lambda 1, lambda 2, so on, lambda n, and the corresponding eigenvectors lambda 1 corresponding to lambda 1, there was a k1 vector, corresponding to lambda 2, there was a k2 vector, and corresponding to lambda n, we had a kn vector. If these solutions form a fundamental set of solutions, if this set is fundamental set, then we can write the general solution as x is equal to c1 x1 bar plus c2 x2 bar plus so on plus cn x n bar. So I hope you got it. If you have any question in the previous lecture, this was a short review of the previous lecture. If you have any question, you can ask me. Otherwise, now we are going to discuss how to find these eigenvalues and eigenvectors. In fact, when we write a system of first order differential equation in a matrix form, we have this matrix A, which is known. And we can find these eigenvalues and eigenvectors corresponding to this matrix A. Now, today we are going to discuss how to find eigenvalues and eigenvectors of a given matrix A. Let me add people. Now, what are the eigenvalues and eigenvectors? If we discuss it geometrically, eigenvalues and eigenvector, like we have a matrix A, which is a 2 by 2 matrix, and it is 1, 2, 2, 4, 1, 2, 2, 4. And we have a vector X, which is 1, 1, 1, 1. If we multiply these two things, A times X, what do we obtain? 1, 2, 2, 4 into 1, 1. What do we get here? 1 into 1 plus 2 into 1. It is 3. And 2 into 1 and 4 into 1. It is 6. What do we obtain here? 3 times 1, 2. Now, if we plot this vector and this vector graphically on an xy plane, for example, this is your x1 plane and this is your x2 plane, then this vector x, which is 1, 1, it is something like 1, 1. यहाँ पे आ जाएगा. So this is this vector. Okay, this is your x vector. You can say this is x. Now, when after multiplying A with x, what do we get here? 1, 2, which is x1 and y2 here. Now, this vector is this one. So this is your 1, 2 vector, and this is your 1, 1 vector. Now, let us assume another vector y, which is 1, 2, 1, 2. Now, when we multiply A with y, A times y, what do we get? 1, 2, 2, 4 times 1, 2. And what we have obtained here, 1, 4, 5, 2, 8, 10. If we common take 5 from here, what do we get? 1, 2. Now, you can see here that the assumed vector is what? 1, 2. And after multiplying y with A from the left-hand side, what do we get? 5 times 1, 2. So if we plot this thing, if we say that this is 1, this is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, 9, 10. Okay. So 1, 2, this is the vector 1, 2, original vector. This is 1, 1, 2. And the resulting vector after multiplying y with A, we get 5 times 1, 2 means 5, 10. So it is 1, 2, 3, 4, 5. Here we have 5, 1, 2, 3, 4. Here we have 1, 2, 3, 4, 5, and here 10. So what do we obtain here? We obtain a vector, which is basically a similar vector till here, and it is what? 5, 10. It is 5 times 1, 2. Now, in these two examples, you can observe that in these examples, what do you observe? That when we have this vector and we multiply A with X, we get a new vector. Its direction has been changed. The original direction of x has been changed. And also the vector x has been scaled. Okay. Now in the second example, direction not changed. Direction not changed. Also, the vector is scaled. Direction change means this vector has been rotated after multiplying a. But this vector has not been rotated, or its direction has not been changed. It is only scaled. So all the vectors, by definition of the eigenvectors geometrically, all the vectors, when we multiply them with some matrix A, and their direction has not been changed, they are only being scaled. Either they have been, you can say, extended, prolonged, or they might be contracted. Okay. Their direction has not been changed except the sign. Okay. The sign can also be changed. Means the other vector, when we multiply with a, for example, y is some vector, and when we multiply a with the y, it only changes its scale. Means it can be prolonged, it can be extended or contracted, or its direction can be changed only in the opposite direction. So such kind of vectors, this one, are called eigenvectors. Okay. You can say that simply, all the vectors, they do not change their direction. They are not rotated, in fact. Okay. Under the transformation of this A is transformation. Basically, this A is going to transform this vector into a new vector. Okay. So then we say that all these vectors whose basically direction has not been changed except the negative sign, and they could be scaled only, these kind of vectors in some space are called eigenvectors. I hope you get it. If you have any question, you can ask. Now, for example, how to find these vectors? According to that geometrical interpretation, we can define that if we have some x vector in some Rn in some space, and A is the transformation. When we multiply A with x, we get the same x with some lambda, which is the scaling factor, of that vector x. It might enlarge that vector. Its magnitude will be bigger, will become larger, or its magnitude will be contracted. Or if the lambda is negative, then its direction will be changed to the opposite direction only. The vector will not be rotated, in fact. So these kind of vectors are basically called eigenvectors. This is the basic definition of the eigenvectors. Eigenvalues and eigenvectors. Eigenvalues and eigenvectors. So these vectors are then called eigenvectors, and this scaling factor is basically called an eigenvalue. This one. And why do we need such kind of vectors and such kind of values? Because whenever you say that geometrically x is some vector, If we multiply this vector with some transformation, which is A is going to transform this vector into some new vector, but it will be only scaled. Either it will be contracted, or it can be basically enlarged, or it can go towards the opposite direction, this one. So you can use such kind of concept in simple harmonic motion. To and fro motions. Wherever to and fro motions are involved, these eigenvectors and eigenvalues have applications. For example, in the spring mass system, we discussed earlier while discussing higher order differential equations. Whenever we have spring mass system, you can you know that there is a motion which is to and fro motions. In to and fro motions, the amplitude decreases slowly with the passage of time in the presence of frictional forces. For example, air is a frictional force while the motion of a spring. So in that case, in all the to and fro motions, the motion is basically the motion of that spring is slightly decreased only. And we can find that motion, and we can use eigenvalues and eigenvectors in order to basically capture the motion of that spring. So there are a lot of other applications where we can use eigenvalues and eigenvectors, but which you have already studied is the spring mass systems. So that's why I gave you an example of spring mass system. I hope you got it. If you have any question, you can ask me. Now, let's move forward. How to find these vectors and values, these scaling values or eigenvalues. Now, this is the basic definition of eigenvectors and eigenvalues. We can take this thing on the other side or this thing on the other side. You can say whatever, A minus AX minus lambda times X is equal to 0. From here, we can take common X. This one is equal to 0. And here we have to put I. Why? Because this is a matrix and we cannot subtract a constant, a real number from a matrix. So we have to put here an identity matrix, which is identity matrix of the same order. Identity matrix of order as of A. So now, what is this? This is basically a homogeneous linear system. Homogeneous linear system, because this is what? This is nothing but a matrix times X. If we call that B times X is equal to 0, where B is what? It is A minus lambda I. This is what we have discussed in the previous lecture while discussing the system of first order differential equation. In order to solve that system, we had obtained such kind of equation. And I told you that this we can use this equation in order to find the lambda, which is eigenvalue, and X, which is eigenvector. Now, if this is a homogeneous linear system, then a homogeneous linear system can have only non-trivial solutions. For non-trivial solutions, what do we do here? This coefficient matrix should have determinant equal to 0. Otherwise, we cannot have non-trivial solutions. I hope you know it from the linear algebra. Lambda times I is equal to 0. Now, we have two equations. One is this, and the second is this. From the equation 2, we know that A is known. It is a known matrix. If we put here the value of A minus lambda is unknown value, eigenvalue, which is to be determined here. I is identity matrix, we know it. Now this determinant, we put it equal to 0. Now this determinant gives us the value of lambda, okay? And I told you this determinant, if we solve it, it gives us a polynomial of degree n. So if it is a polynomial of degree n, then it must have n eigenvalues. For example, lambda 1, lambda 2, so on, lambda n. And by inserting the values of lambdas one by one here in this equation, lambda 1, lambda 2, lambda 3, lambda 4, and so on, lambda n, we'll get n linear systems. And after solving these linear systems, we can obtain an eigenvector, for example, k1 corresponding to lambda 1, and k2 corresponding to lambda 2, so on, kn corresponding to lambda n. Okay, this is how we can find eigenvalues and eigenvectors. Once we know the eigenvalues and eigenvectors, then we can write the n solutions of the given system of first order differential equation. And I told you what are the solutions of this system. We can write them. X1 is the first solution, which is the first eigenvector times exponential of first eigenvalue times t, and so on. We can write the n solutions. And then finally, we can write the general solution after investigating whether these n solutions are linearly independent and they form the fundamental set of solutions. Now, now the question is, what happens if we are unable to find, for example, if the eigenvalues are not distinct, real and distinct? So in order to further discuss the eigenvalues, types of the eigenvalues, we need to discuss different cases when the eigenvalues are real and distinct, and eigenvalues are repeated, and so on, some other cases. Let's discuss these things with the help of examples. First example, this one. For example, find the general solution of the first order system. The first order system is dx by dt is equal to 308 minus 1 times x1, x2. This is the system. What is the matrix? This is your matrix A, and what first we have to do, we have to find its eigenvalues and eigenvectors, and we can first we need to find, or we have to find, eigenvalues and eigenvectors, and eigenvectors of the matrix A, of the coefficient matrix A. How can we find them? First, we write the characteristic equation. I told you the characteristic equation is what? It is that determinant equation, determinant of, determinant of A minus lambda I. We put it equal to 0. Now, what is this equation? Determinant of A What is A? It is 3, 0, 8 minus 1 minus lambda times I 1, 0, 0, 1, and its determinant equal to 0. So it is 3 minus lambda 0, 8, and minus 1 minus lambda. So its determinant, okay, we get this equal to 0. There are people who are waiting to. Now, after solving this, what we can write here, 3 minus lambda and minus 1 minus lambda minus 0 is equal to 0. So what do we get here? Lambda is equal to, maybe this one is minus 1 and this one is 3. We obtain 2 eigenvalues. Now, the case 1 is when eigenvalues are real and distinct. Real and distinct. You can see that the eigenvalues are real numbers and distinct here. In that case, we can obtain always 2 linearly independent solutions, x1, which is k1 times e raised power minus 1t, which is lambda 1 here, and the other solution, which is k2 e raised power minus plus 3t. This is your lambda 2. If the roots are real and distinct, we can always find linearly independent solutions corresponding to each eigenvalue. Now we are going to find the corresponding eigenvectors from the equation A minus lambda I times x is equal to 0, where the first case when lambda is minus 1, when lambda is, or lambda 1 is minus 1, we suppose that, or we assume that x1, or you can say k1 is the eigenvector corresponding to first eigenvalue lambda 1 is equal to minus 1. That is, you can say that k1 is what? It is, you can say small k1, small k2. This one. Now, if we insert lambda 1 is equal to minus 1 here, x should be replaced with the k1. So what do we obtain here? A minus lambda is now minus 1 times I times k1 vector equal to 0 vector. It's 0 vector in fact. Now, after putting the values here, A is what? It is 3, 0, 8, minus 1. This is your A. And the minus plus I, 1, 0, 0, 1. This whole times k1, k2 equal to 0, 0. Now, after solving this, what do we obtain here? We obtain 3 plus 1 is 4. 3 plus 1 is 4. 8 plus 1 is 8. 0 here, 8. Minus 1 plus 1 is 0 again here. And we obtain k1, k2 is equal to 0, 0. Now, this is your homogeneous linear system. And we need to solve it now. How to solve it? We write the augmented matrix corresponding to this linear system, and it is 4, 0, 0, this 8, 0, 0. And we try to reduce this into echelon form. I hope you know what is echelon form or reduced echelon form. Everybody knows what is echelon or reduced echelon form? I hope you know it. Uh, if anybody doesn't, he can ask me any question. Echelon form, reduced echelon form, you have already studied in your math 120, I think, linear algebra course. Now, we are going to reduce it now into echelon form. What do we do here? We multiply this equation by 2 and subtract from this. Okay, R2 minus 2R1. And we are going to change R2. So it becomes 4, 0, 0, and this becomes again 0, 0, 0. Now this is in the echelon form. Now we can obtain from here, from this system, we get 4k1 plus 0 is equal to 0. And the second equation is already 0. So from this equation, we get k1 is equal to 0. Now, what is the value of k2? What is the value of k2? We are unable to find k2 here. So k2 is a free variable here. If k2 is a free variable, we can assume that k2 is some t, where t belongs to R. So now we have all the values of these components k1 and k2. So we can write the eigenvector k1 as 0, t, and ultimately we can take common t as 0, 1, and where t belongs to R. So our eigenvector is basically this. K is this without the t, because t is the parameter. All the vectors are basically generated by this vector. All these k vectors, k1 vectors, they are generated by this vector, because here we have a t. So the only vector which generates that eigenspace, आपने linear algebra में पढ़ा होगा. These vectors basically they generate eigenspaces, but we take only the vector which is basically the basis for that eigenspace. So this is the main vector which generates that K1 space, eigenspace. There's a question in the chat window. G, talk to me. Who is this?
सर ये जो पैरामीटर आपने k2 is equal to t लिखा है ये डिफरेंट है ना फ्रॉम द इंडिपेंडेंट वेरिएबल जो शुरू में हमने dx over dt लिखा
Oh yes, we should not write t here because t is independent variable. So we can use some other variable here, maybe s. So this should be different. This should not be that same as independent variable. So this is s, where s belongs to r. Okay? So this is obviously a different parameter. Now, our k1 vector is 0, 1 vector, in fact, which we are going to use for writing the general solution or to obtain the linearly independent solutions. If k1 is this, then our first solution is what? It is k1 times e raised power lambda 1 t. So k1 is what? It is 0, 1 times e raised power minus 1 t. So this is your first solution. Now for the other value of lambda, which is lambda is equal to 3, we are going again in a similar way, we are going to find the k2, which is the second eigenvector, and I hope you can find it on a similar manner. And finally, you should obtain another vector, maybe as r times 1, 2. Okay. So ultimately, we are going to use k2 vector as 1, 2 vector, and your lambda 2 is what? It is 3. So ultimately, your second solution is what it is? 1, 2 e raised power 3t. So this will be your second solution. Now, corresponding to two eigenvalues, we obtain two eigenvectors. So what we are going to check now, we have two solutions now, okay? The two solutions, x1 and x2, we are going to check whether now this forms a fundamental set of solutions or not. For that, what we do is a fundamental set, okay? Fundamental set of solutions. We are going to check this now. How do we check whether this set of solutions are fundamental set? We are going to check whether these two solutions are linearly independent or not. Okay. For that, what we do, we need to find the Wronskian, and Wronskian is what? It is nothing but what was the first solution? It was 0, 1, means what is this? It is 0, e raised power minus 1t. And the other one is what? It is e raised power 3t and 2 e raised power 3t. These are basically the solution. K1 को हम यहाँ पे लिखेंगे 0 e raised power minus t, and K2 को हम इसके कॉलम को e raised power 3t and e raised power 2 e raised power 3t. This one. Now, we need to find this determinant, and this determinant, it is 0 minus this into this. It is negative e raised power minus t and 3t, it becomes 2t. Now, exponential function is never t for all values of t belongs to R. So Wronskian is non-zero here for any value of t belongs to R. So our solutions x1 and x2, they are linearly independent solutions. If they are linearly independent solutions, they form a fundamental set of solutions. Yes, G, Ali Hamza, you have any question? No? Okay. If x1 and x2 now, they form a fundamental set of solutions. If they are, then we can write the general solution by writing, where should I write it? Let me raise this thing. Then the general solution, solution can be written as what? X is equal to C1x1 plus C2x2. And what is x1? It is nothing but 0, 1 e raised power minus t plus C2, and the second is 1, 2 e raised power 3t. So this is your general solution of the given system first order differential equation. Now, if we are given in some initial conditions, we can find these constants C1 and C2. Okay, if we are given initial condition corresponding to each equation in that system, then we can find the values of these constants also, and we can obtain finally the solution corresponding to that initial value problem. I hope you get it. If you have any question, Ji Daniel, come on.
यस सर, मैंने बस ये पूछना था, ये जो हमने S और R को बीच में डिस्कार्ड किया, ये जब हम जनरल सॉल्यूशन लिखेंगे तो ये C1 और C2 में होंगे एडजस्टेड?
देखें, पहले में क्या आया था S, यहाँ पे S लिख लें आप. दूसरे में क्या आया था R, यहाँ पे R लिख लें. S is a constant, C1 is a constant, so they are arbitrary constant. So we can write this one C1 S is D1 constant, okay, and it is multiplied with x1, again the solution, and the other constant becomes D2 constant, and it is basically again multiplied with the x2. So it doesn't change anything, you write that constant or not, because that S is also an arbitrary constant which belongs to R, and C1 is another constant which belongs to R, which is also an arbitrary constant. So multiplication of two constants become a new constant. Okay, and that constant can be, we can find that constant by using initial conditions if they are given in the system corresponding to each equation. This doesn't change anything. I hope you get it.
Yes, sir. समझ आ गया.
ठीक है? Any other question? Now, this was the case one. The case 2 is when the eigenvalues or some of the eigenvalues are repeated. Then what do we do here in that case? In the case 1, when the eigenvalues are distinct, real and distinct, then we can write the solution in this way. Okay, I told you in the previous lecture as well for a general value. Now, if we have n eigenvalues, but first k values are identical. First k values out of n. So this is basically lambda 1, 2, 3, so on k, and the rest of k, lambda k plus 1, and lambda k plus 2, so on lambda n. The last value will be n. The first k values are repeated. Then how to write the solution in this case? In this case, when some of the eigenvalues are repeated, then there are two further cases in this case. Two further cases. The first case is now lambda is an eigenvalue which is repeated k times. In that, we also have two cases. Case 1 is lambda is repeated k times, and we can find k eigenvectors corresponding to one eigenvalue. We can find k eigenvectors corresponding to lambda. Means eigenvalue एक है, k times repeat हो रही है, लेकिन जब हम उसके eigenvectors ट्राई करते हैं फाइंड करने की, तो हमारे पास k eigenvectors आ जाते हैं. ठीक है, this is the first case. The second case is lambda k times repeat हो रही है. We can find only one eigenvector corresponding to lambda. ठीक है, अगर तो आपके पास आइगन वैल्यूज लैम्डा जो है वो k टाइम रिपीट हो रही है और उसके कॉरस्पॉन्डिंग हमारे पास k आइगन वेक्टर्स आ जाते हैं, तो फिर तो सॉल्यूशन उसी तरह लिखेंगे जैसे कि हम रियल एंड डिस्टिंक्ट के केस के लिए लिखते थे. ठीक है, लेकिन अगर आपके पास केस 2 आ जाता है कि वी कैन ओनली फाइंड ओनली वन आइगन वेक्टर कॉरस्पॉन्डिंग टू लैम्डा, देन इन ऑर्डर टू फाइंड n linearly independent solutions we should have what n linearly independent solutions. So sorry, in order to write the general solution we should have n linearly independent solution. In that case we must find k minus 1 more eigenvectors, because हमारे पास यहाँ पे k आइगन वैल्यूज हैं, एक आइगन वैल्यू k टाइम्स रिपीट हो रही है, तो हमारे पास k आइगन वेक्टर्स होने चाहिए इन ऑर्डर टू राइट द जनरल सॉल्यूशन. अगर तो लैम्डा रिपीट हो रही है k टाइम्स और उसके कॉरस्पॉन्डिंग k आइगन वेक्टर्स आ जाते हैं, मसलन अगर लैम्डा 3 दफा रिपीट हो रही है तो आइगन वैल्यू के उस आइगन वैल्यू के कॉरस्पॉन्डिंग 3 आइगन वेक्टर्स आ जाते हैं, तो वी डोंट हैव एनी इशू. ठीक है, लेकिन अगर लैम्डा 3 दफा रिपीट हो रहा है और उसके कॉरस्पॉन्डिंग एक आइगन वैल्यू एक आइगन वेक्टर आता है, तो बाकी दो आइगन वेक्टर 3 - 1 वो हमें फाइंड करने पड़ेंगे. ठीक है, हम कैसे फाइंड करेंगे, we'll discuss this in the next lecture. And it's time for the quiz. Quiz has been uploaded on the same LMS page, quizzes, test and quizzes. If you have any question, for now, you can ask me, otherwise you can start the quiz. You can go and download this quiz and start solving it.